We are solving question number 58 of GATE 2022 related to the subject of process control and instrumentation. And the question is, in the block diagram shown in the figure, the transfer function g is equal to k upon tau s plus 1 with k greater than 0 and tau greater than 0. The maximum value of k below which the system remains stable is dash, rounded off to 2 decimal places. So in this given question, we have been given a block diagram and have been asked to find the maximum value of the constant k for which the system remains stable. So to solve the questions, let us find the closed loop transfer function of this entire block. Once we have this closed loop transfer function, then we can use this roots criteria or any other rule to check for the stability of the system. So over here, the main output is y. And so in this node also it will be y, and in this line also it will be y. So let's just call this as y1 and this is y2. That is, we can rewrite this as y is equal to y1 plus y2. Now y1, we can see that u is passing through this transfer function block of g, and then we are getting y1. That is, we can write y1 as u times of g. So we can replace that as u into g plus y2. The value of y2 we have to find by solving this block diagram. That we will do. So let's just call. So over here we have this y2. Now we have this transfer function block of g. So let's just call this as u. Let's just call it as u1. And the other block diagram from over here will be, since this is y, g, and over here it will be y into g. So we have this value. Now we need to find the value of the input at over here. Then we can simply sum to find this u1. So u1 will be same across all these three directions. That is, we can write u1 as something unknown. Let's just call it as y double dash plus y times of g. Now we can see that since this is u1, over here we will be having u1 into g. Similarly, at this point we will be having u1 g into again multiplied by this g. So it will become u1 g square. That is, our y double dash is u1 g square. That is, we can replace it over here and it will become u1 is equal to u1 g square plus y g. Now from over here we can find the value of unknown u1. So it will become u1 minus u1 g square plus y times g. You can take u1, it will be is equal to y times g, and you can take u1 common. 1 minus g square is equal to yg, and we will be having u1 is equal to yg upon 1 minus g square. Now we have this value of u1 over here. So now we need to find this value of y2. So y2 will be simply this u1 times of g. So it will become y g into 1 minus g square into g. So it will become yg square upon 1 minus g square is equal to y2. Now we have this value of y2, so that we will replace it in this equation, and we will be having y is equal to ug plus y2 ug plus yg square upon 1 minus g square is equal to y. So from over here we can write this as y into 1 minus g square 1 minus g square is equal to ug, and simplifying this we can find the value of y by u as it will become g 1 minus g square upon 1 minus of 2g square. So over here we have this closed loop transfer function, that is for this entire block diagram we have this transfer function as g into 1 minus g square upon 1 minus 2g square. Now for stability, we can use this root array which states that if we have this characteristic equation which is defined as, so in this case the characteristic equation will be denominator, that is 1 minus 2g square is equal to 0. Then we have this root array on the basis of which we can comment on the stability of the system. So is the characteristic equation over here we are having 1 minus 2g square is equal to 0, and g we have been given as kp upon tau s plus 1 over here. So we can just simply replace that value and simplify to find a polynomial form of this equation. So it will become tau s plus 1 whole square minus of 2k square is equal to 0. That is tau square s square plus 2 tau s plus 1 minus of 2k square is equal to 0. So this is our main equation. So now we will be using this root array to comment on the stability. So from root array we know that if the value of the first column, so if this is greater than 0, that implies the system is stable. So we will be using that. So the characteristic equation that we have is tau square s square plus 2 tau s plus 1 minus 2k square is equal to 0. So we can compare this with the first order polynomial in terms of a, and we will be getting the value of a naught as a naught is equal to tau square, then a1 is equal to 2 tau, and then a2 is equal to 1 minus 2k square. Similarly, this a3 will be 0, and all this value we need to find out. So let's just calculate the value of a1. a1 is a1 a2 minus this entire term, so it will become 2 tau into 1 minus of 2k square minus of tau square, and a3 is 0, so this will become 0 upon a1. So a1 we are having tau square, so this will become 2 tau to 1 minus 2k square upon. So over here in the denominator we are having a1, so a1 over here we will be having 2 tau. This is 2 tau. That is capital A1 will be 1 minus 2k square. Now if you look into this second term, that is a2, since a5 is 0 and a4 is also 0, so this will also become 0, and we don't need to calculate the other terms. We can just comment on the basis of this first three term. So a naught is tau square, that will always be, that is a naught is tau square, that will always be greater than 0. a1 is 2 tau, that will also be greater than 0, since we have been given that tau is greater than 0. And now for the system to be stable, we have to, that a1 should also be greater than 0, that is 1 minus 2k square should also be greater than 0. So on the basis of this, we can write 1 is greater than 2k square, that is from over here we will get the value of k should be less than 1 upon root 2, that is k should be less than 0.707. So the final answer, we can report it as the maximum value of k below which the system remains stable is 0.70.